So, before we go in here, we're going to keep using the files we did last class, probably for today. I don't know how much time we'll have or how quickly we'll move. If we have enough time, I might start on the next topic, which is interaction terms. We'll definitely go over these on Thursday and then kind of continue with those into next week. So we're starting to get the topics that aren't covered. We can't cover them quite just a week. So usually they'll kind of go over, put 9 and 10, 10 and 11, kind of either 3 class periods, or eventually someone might spend 2 full weeks on it, right? So a couple updates to Canvas. I don't have your exam factored into your grade yet, because what can you still turn in by the end of the day today? No one knows. Yeah.
It's the extra credit, but it's due at 1:45.
Oh, did I have it set to be before class? Well, here. We'll make it by the end of the day. I meant to have it due before the end of the day. So kind of get some additional time to work on it. So where's that at? Where are we at? I might have changed my mind. Yeah, here. If you want to put some last minute touches on it, because I won't be able to get to grade it today. So I'm okay having it being due at the end of the day. Let's just update this. I'll put, hopefully you're not working on it this late, but just due by the end of the day. I won't be able to start grading them until tomorrow anyways, so I'm kind of okay. Rush to get it done. So a couple things you still weren't sure on. Feel free to kind of revisit it and kind of re-upload it by the end of the day today. Okay. So once I grade those, I'll add those to the grade. So once again, I will try to grade those tomorrow. I don't know if I'll get through them completely. Although, to be honest, I'll probably start with your section. So your section will probably be done tomorrow. But you'll see those grades. If I do get them completed tomorrow, you'll see your grades kind of have that new exam score with your extra credit points added in, kind of get updated on Canvas, and then kind of be reflected in your grade, where it counts for, I think it's 32% of the overall grade. So I'll kind of adjust those. So you'll start to see where you're currently at in the class. I'll also I'll figure out your grade tool so you can start to play around with, okay, if I miss an assignment, but if I can increase my problem set grade to this, if I can increase my quiz grade to that, if I get this on the final, what would my hypothetical grade be in the class? I'll go over that kind of tool a little bit more on Thursday, but you might see that pop up tomorrow as well as I'm posting these new exam scores with your extra credit added in, okay? Other than that, right now, there's nothing up there, no quizzes, no problem sets. I've got a quiz kind of ready to go. I think that we'll cover everything that you'll need to go to answer that quiz, so I'll probably post that once I get back to my office this afternoon. You've got that set of practice problems that I put up there the end of last week. Somewhere around here. Yeah, so there we go. Those sample questions for. If I release that today, I'll probably have it set to be due next Thursday's class, so like a week and a half to kind of work on that, get that quiz completed. And I'll not mention that on Thursday as well, but you'll see that pop up after class today. You'll have that quiz will be due at the end of the day of next Thursday. I had to shift my office hours around a little bit this week. I think I mentioned this to you. I did a similar thing for you guys. My other courses have an exam. So tomorrow's office hours, I'll have a room reserved. And I'll only be going over like exam review with them. So for you guys, if you do want to meet, I will be available by appointment tomorrow morning. So I'll be around all morning. Although I can't imagine, like, there's not a whole lot that's out there right now that you probably have a lot of questions on. There isn't a problem set. Although along with the quiz, once again, I think we'll cover all the material today in class. You'll see the next problem set pop up as well. All right, so similar kind of thing. I'll probably give you to the end of the day Friday for that. So just an additional day. They'll probably have some additional office hours next week. And then Friday, I can meet virtually for office hours, but I won't physically be on campus. So if you do want to meet this week, send me an email. We can schedule a time sometime tomorrow before 12:30. Or if you want to meet virtually, we can do that Friday. I should be available kind of most of the day into the late afternoon. Okay. Other than that, I think that should be all the housekeeping stuff. Any questions for me before we kind of dive into material here today? So later this afternoon, you'll see that next quiz, next problem set pop up. It'll be focused on not interaction terms. That's what we're going to be talking about next, but it's going to be simply over these nonlinear relationships. Okay. So we started out with the quadratic. We then moved. Why do I have 2 pulled up here? Well, let's get rid of this one. So we talked about kind of quadratic relationships, even cubic. we then started to move towards what we were calling these logarithmic relationships, right? So we had linear log, log linear. Just kind of a quick and kind of dirty review. What did these look like? So if we're thinking about that unit changes might not matter as much as percentage changes do, we could use a level log model. Remember that first word is always my what variable. Oh, it's not focused. Does that look better? Okay. So the first word kind of lines up with the way that we write our regression equation. So this would be my y variable. The log is my x variable. So I'm thinking about, I'm trying to estimate something that I think has a nonlinear relationship, that it's not unit changes in x that matter, but percentage changes. So I'm going to take the natural log. We said now the interpretation of our slope coefficient is what? A 1 unit change in x. I'm taking the natural log. What am I trying to get? Not level changes, but percentages. So it's no longer a 1 unit change in x. It's a 1 percentage change in x. And the effect that it's going to have on my y variable, so it's going to cause my predicted y to change by what? Not just beta 1, but if we're going from, and I said this isn't kind of perfectly technically correct, but if I'm looking at going from like a percentage to a unit, this is like going from percentage to a probability. What do I need to do to my coefficient? So if I'm going from percent to probability, I need to, how do you convert a percent into a probability? You divide by 100, all right? So the change that we would see in our predicted y variable is not just beta 1, but beta 1 over 100. And now, because we've got y's in units, it's changed in beta 1 over 100, whatever the units for y is. We also had, so any questions on that before we kind of keep moving here? Kind of summarizing where we left off. So once again, now if I had a log level relationship, I'm thinking about, okay, x, the unit changes make sense, but it's likely it's going to cause different percentage changes in y, right? So, maybe going from a, 75 to an 80 on the exam isn't the same as going from a 95 to 100, right? That was a kind of different percentage changes there. So now I'm going to estimate this relationship, but I wanted the percent changes in y, so I need to be taking the natural log of y. And here I'm just thinking about still x is in units. So now what's the interpretation of my slope coefficient? It's a 1 unit change, kind of this triangle representing change, right? And x would cause my predicted, is this still on the screen? Yeah. Y value to change by not just beta 1, but here if I'm going from units to a percentage, I would need to multiply by 100, because now the changes in y represent percentage changes. Okay. This is just my general interpretation of these level log level. We'll work through some more examples and stay here today where we have some actual variables. This is kind of where we left off. Okay. Any questions on this before we keep moving? Okay. So we'll look at some models here in a second, but one thing that I want to go through before we get there, so we kind of did this last class with college GPA. I guess my animations are turned off. So let's say I'm thinking about, I want to test for whether or not changes in these two variables might be logarithmic, or that percent changes matter more than linear change. So I've got this college GPA as my y variable. I can use this joint significance test that we've talked about to test for whether or not kind of the relationship could be linear or nonlinear. So we'll talk about some downfalls of this method, but for now, what we'll do is we'll try to predict our y variable, college GPA, using both the linear terms and these kind of logarithmic terms. So it's like holding constant the level of SAT. What would be the effect of a percentage change from that point B? Right? So we're going to be able to estimate this relationship altogether. We can then perform 2 F-tests. are the linear coefficients both equal to 0? So if we fail to reject that, what would that be evidence of? So if I've got the coefficients on my linear terms and I fail to reject that they're jointly significant, basically I'm saying those coefficients are 0, that's evidence that the relationship is actually. So if I'm saying the linear terms have no effect, that's evidence that one model is a better predictor, not the linear model, the percentage or the non-linear model. Now, if I run my f-test for the coefficients on my non-linear terms, my logarithmic terms, and I fail to reject there, okay, well, they're both equal to 0. They don't have a significant relationship for predicting y. That would be evidence that the linear model is a better predictor. So all we're going to do is go to stay here. I think where we left off in the code. So I'm going to expand this, scroll down. We are using this GPA data. So I don't think I have my file path set right. So where do I have this? Oh, did I put this on? Let me make sure. Oh yeah, I've got it up there on Canvas. Okay, I was gonna say, let me make sure that's up on Canvas. I think I just forgot to put it in my. Yeah, I put it in this general file. Okay, so I've got my GPA data here. We talked about this last class. I generated this new variable where I was taking kind of the natural log of high school ranking. Although, let me make sure. I think in the slides we had, oh yeah, high school ranking and SAT scores. So just making sure this lines up. So I'm going to create this new variable where it's just the natural log of high school rank. And I just use that ln function, right? Taking the natural log. We don't need to run these regressions right now. I'm also going to kind of generate the natural log of SAT. I don't know if we're going to use that, but I want to make sure that I run that. So I'm going to come down here. Is that what this was? Yeah, SAT. So we are going to use that. So we've now got these two variables, these X variables, SAT scores and high school ranking. We're interested in whether or not we should be modeling them as linear relationships to GPA or nonlinear. So what we're going to do is run this regression, right, where we include both the linear terms of these two variables, but also these natural log terms. So I'm going to run that regression. Now, we're thinking about joint significance here. If we were just to look at these coefficients, we kind of have a problem. Which of these would we say are statistically significant at any of our benchmark levels? Which of these variables? All of them have a p-value of. So are we going to reject or fail to reject all of them? The p-value is 0, you should reject, right? It's going to be less than alpha. So I kind of have a problem, right? If I just try to run this model and just use individual coefficients. So what I'm going to do instead is run this f-test. What it'll do is run a restricted model where it leaves out those linear terms and says, okay, was the unrestricted model where I include all these, was the restricted model actually better, right? Was the restricted model where I left out these linear terms, was it actually a better predictor? Now we know when we add in variables, what always has to happen to our R squared? It always increases, right? So it's going to run that restricted regression behind the scenes just for the sake of being able to see. I'm going to go ahead, copy and paste this, and I'm going to run the restricted model where we leave out the linear terms so we can have a comparison here. So if I don't run the f-test yet, but I'm just looking at my restricted and my unrestricted model. So that restricted model, where I left out those linear terms, I've got an R squared of 0.25, right? 0.256. Now, when I include these two additional variables, the linear terms, yes, my R squared is going to go up. We know when we add in more variables, my R squared has to go up. But it's almost like we're thinking about, okay, we know we added two more variables, R squared is going to go up, but did it go up in a way that almost, this isn't a perfect way of thinking about it, but it's like, does the percent of the variation per variable we're using, has that went up, right? Because I can always explain more variation if I go from having 2 to 100, but per variable I included, did I see the amount of variation I could explain go up? So that's kind of what our f-test is doing. So we use that test command. We're first going to test for whether or not leaving out these linear terms, right? If that unrestricted model, right, where we kept all of them, is actually better, right? So I look here, if I leave out both the linear terms, I'm rejecting the null hypothesis. So if I reject the null here, it's that both of these coefficients on the linear term are equal to 0. So if I reject that, what am I saying? That these linear terms are jointly significant, or that they were essentially good predictors, right? Or they were increasing my R squared, right, at a statistically significant level. So this would be evidence that the linear model might be better at capturing the relationship between these two variables in college GPA. Any questions on that before we keep moving? Now, I can also run a test where I see, okay, does the added terms of the natural logs, right? Does that change anything? So here I'm thinking about if I were to run a restricted model where I left out those natural log terms, right? So I had an R squared of 0.238. If I include them, my R squared goes up to 0.26, right? So I saw a larger percent change in my R squared. So if I run my kind of F test for the nonlinear terms, well, I can reject that as well. This is a good example where if you run these F tests for the linear and nonlinear, sometimes you can reject both, right? Or I found evidence that both models here are good predictors. Now, if I wanted to choose one, what's something I might look at? So notice here, this was the joint significant test for the nonlinear terms. So we're assuming their coefficients are equal to 0. We can reject that at a high level of confidence. The p-value is 0. Problem is, when we did the F test for the linear terms, it also had a p-value of 0. However, if my F stat is 22, when I looked at the test for my nonlinear terms, and it was 73 for the nonlinear terms, which of these p-values is actually smaller? Even though I can't tell from the output which one has to be smaller. Nonlinear, why? Yeah, if I have a test statistic, whether it's coming from a student T, standard normal distribution, I just found two test statistics. One was 22, I'm rounding these. The other was 73. The p-value here has to be less than the p-value from the other one. So which one of these can I reject with higher levels of statistical significance? It would actually be the nonlinear model. That was the one that had that higher test statistic. So if I had to choose between, so we kind of thought about here our, so we had, what was it, SAT and high school rank. And then we had the natural logs. If I had to choose, I would choose the one that has a higher test statistic because inherently it would have a higher level of significance or a lower p-value. But in theory here, we don't really have, we have evidence that it could be either one, right? This might be a close one. Sometimes that won't be the case. You can clearly only reject one of the restrictions, but in this case, we actually have rejected both, right? But this would be the procedure that you would use to determine kind of whether or not you should be including these additional nonlinear terms, okay? Any questions on this idea before we keep moving here? All right. We'll stay in this data set for one more example. And I think I might have gotten through this in the last class. Maybe we didn't. And let's make sure I took the natural log of GPA somewhere. I don't know if I did. Oh, right here. So now I'm going to also take not only the natural log of my high school ranking and SAT scores, I'm also going to take the natural log of my dependent variable. So if I take the natural log of GPAs, I then run this regression where I've got GPAs, the natural log of GPA, and the natural log of SAT scores. How would I interpret that coefficient? So I think about these two models. Oops, I need to actually create that variable. There we go. So the linear model, where I was trying to predict, we had what? A log level model. I had an R squared of 0.1285. Now, if I look down here at the what we would call a log model, right? There I've got an R squared of what? 0.1239. So it's actually a little bit lower. So just looking at the R squared, it would suggest which of these models should I be using? The log linear or the log log? Well, is explaining more variation a better or better or worse? Like pulling teeth, guys. If my R squared is higher, that means I'm explaining a higher amount of variation. Is that a good thing or a bad thing? Good thing, right? So which of these models is explaining more variation? It looks like it's the log level model, right? Not the log log model. Now, what I could also do is not only look at the R squared, similar to kind of what we did for the F statistics, I could look at my p-values or my test statistics. Well, once again, my p-values in both models for the coefficients are both 0. However, which of these has a slightly higher test statistic, which inherently means we know the p-value will be a little bit lower? Well, it looks like my linear term slightly higher than my nonlinear term. To determine which model we can use, we can run both models, compare the R squared, or we compare the statistical significance of the two coefficients from the two models, right? There, if we're looking at the statistical significance, we want the one that has a higher test statistic inherently then also meaning a lower p-value, right? It's more statistically significant, okay? So those are the two things that like in a problem set or a quiz, I might ask you to identify that tells you which model is better. You're comparing the R squared or you're comparing the statistical significance of the coefficients between the two models.
So questions, so when you're interpreting that second one to percent and both of it.
Yeah, so I've introduced it. How do we actually interpret these coefficients? So just in general, and then we'll go back to the example and think about it. So here, if I take the natural log of college GPA and I predict that with the natural log of SAT scores, it's going to be, well, what? Not a 1 unit change in SAT scores, but a 1% change in my SAT score will cause my predicted what? GPAs, college GPA, to change by what? Well, I'm going from a percentage to a percentage, so do I need to change anything? No, so the change is going to be beta 1, but it's not in the units, right? GPA isn't going up by beta 1, it's going up by beta 1%, right? So with logs, it's kind of nice because everything's in percentage. We don't have to do any kind of, it's just like going back to level. We don't have to do any type of scaling of our coefficient estimate when we interpret it. I think I might have mentioned this last class. So what might this be like a good thing for estimating? The percent change in X causing a percent change in Y. What if X was price? What if Y was quantity demanded? I would have a what here? Elasticity. So we can start to do things like calculate. I might try to get something like this so we can actually see this. I'll try. The second half, I try to start relating things to stuff you would see like in other econ courses. How do we use these statistical tools and apply them to other kind of economic concepts? You know, I could even do something like this where I can control for income. Now, what would this tell me? A 1% change in income causes this percent change in quantity demanded. This would be my income elasticity. But the reason why it's so much more powerful is because now I can estimate an income elasticity. When you were doing this like in your intro or intermediate classes, you're looking at like changes in income and changes in price. But when incomes change, what's likely also always going to be happening is other things change as well. So inherently in those quantities that you had, it's not just the effect of income. You were seeing the effect of income changes, but maybe prices change, maybe all these market conditions change. We can now control for those. We can take controlling for the same exact price, right? But we had a 1% change in income. Now, what is the effect on the percent change in quantity demanded? So we can actually get a better idea of whether or not these are normal or inferior goods. You could have other good prices in there. So you can start to estimate cross-price elasticities of demand. And this becomes like a very powerful, useful tool using these log models in economics. Yep. Any questions on this before we keep moving? Okay. So the next thing that we're going to do, let me think what I want to do here. I mentioned some of this already, so we'll go through the slides a little bit, then we'll kind of come back, do some more work in Stata, kind of taking a break here. So we already looked at these log linear models. You know, once again, we multiply by 100, right? Because we're going from a level to a percentage. We need to multiply that coefficient to kind of interpret it. And it's going to represent percent changes in y now when we're taking the natural log. And then when we had these log models, everything was in terms of percentages, so we didn't have to scale that coefficient at all and make our life easier. It's kind of like a summary of what we talked about. Now, one thing that I want to point out when we're looking at these natural log models, what can I not use for my dependent variable? Let's go up here, but I can't take the natural log of what value? 0. So I can't use dummy variables, right? In fact, also by negative values, that would present a problem to me as well. And so I could do something like take the absolute value, but we won't dive into those kind of issues. It makes it a little more complicated. But yeah, we can't use dummy variables anytime we want to take these natural logs. Okay. We have different methods of still being able to estimate nonlinear relationships with these dummy variables, but we won't talk about that for a couple weeks. Okay. All right. So that's what we were just looking at, kind of those logarithmic log models for college GPA. So I already mentioned this. All right. But if we're running these different models and we want to compare, so let's say we have the polynomial specification. So I want to look at quadratic models where I had a square term, maybe a cubic term as well. I can actually compare and contrast those to my log linear models, right? Or I can compare those to my log kind of, right? I said something slightly incorrect because why can't I compare, say, a linear model to a log linear model by simply comparing my R squared? When I take that natural log, essentially my y variable is no longer the same, right? I've transformed it in such a way that the amount of variation that even exists in that variable has now changed. So I can't compare anytime I have dependent variables that are different. I can only say compare, well, we can think about it. I'll give you a summary list. It might be helpful as opposed to just talking through it. So if I had a level model, right? So this is just like y is equal to x, right? What can I compare that to using my R squared? Well, I could compare that to a level log model because there I'll have the same variation in my y variable, right? Because it's still in levels. What I could also compare to these models, maybe it's not that the natural log model is a better fit. Maybe I'm using, I'll call this a quadratic model or a polynomial model. So this would be where I'm trying to predict y, but I'm including, to this last class, a squared term for that x variable. Or we could even compare that to a cubed model, right? Different levels of quadratic. We can even go up, we can go up as high as we wanted technically, right? Add a fourth term, a fifth term. Here, I'll kind of keep it to just squared and cubic models. I don't want to make it any more complicated. So we can compare all these three models by simply comparing the R squared values because we get the same variation. Now, slight caveat to that, I probably wouldn't want to be just comparing my R squareds because which of these is inherently always going to, so two of these, I can always say one of them is going to have a higher R squared than the other. So what two models here could I definitely say the one is always going to have a higher R squared than the other? The quadratic model compared to our level or our linear model, right? The thing is linear here. So why? Well, because it includes x, but also additional terms. It's almost like I'm adding in more variables. So instead of the R squared, what's probably a better comparison or a better statistic to make comparisons, I should say, between these three models? Not our R squared, but what would account for the fact that I'm including different additional variables? Adjusted R squareds. All right. So it's probably better to kind of use that adjusted R squared, especially when we're comparing this quadratic model to kind of our level or our level log models. Okay. Any questions on this idea? And then the only other ones we talked about. So if I had a log level model, and I'm saying level here, I think in the slides sometimes I think I'm saying linear. Those two terms are interchangeable. So I'm probably gonna go back and forth between the two because that's just, I can never keep it straight in my brain. I've learned it one way and I've seen it a million, the other way a lot. So it's level, linear, it's kind of this referencing the same thing. So if I have a log level model, I can compare that to my log log model by comparing the R squared. Now here, I don't really have to worry as much because I've got kind of the same number of variables here. So I can compare my R squared or my adjusted R squared. It should always be that adjusted R squared. Like they should always tell me the same thing because they both have the same number of variables, right? So it doesn't really matter when I'm making these log level, log log comparisons if I use the adjusted R squared, the R squared to make a decision about which model is better. But I can't compare these models to these. Why? Because the variation that's going to be existing in my Y variable is different. I've taken the natural log, I've transformed the amount of variation that exists, right? So I can't compare those models just based off the R squared. Any questions on this before we keep moving? What's another issue that could arise even between my linear, my level model and my linear log or my level log model? So if I'm taking the natural log of X, let's say I had income was my X variable. What might happen when I go from the level to the level log model? What's something that might change that we're often worried about changing our statistics, things like standard errors or our adjusted R squared. When I take the natural log, what can I take the natural log of? If somebody has an income of 0. So if I try to run that regression, what's going to happen? State is going to automatically kick out those observations. So I could end up with different sample sizes across the two, in which case I should be making comparisons, right? I've got different samples. If I'm thinking about income, well, who did I kick out when I said I can't take the natural log of 0? Anyone who is unemployed. So if I'm worried about estimating something like, I don't know, the level of unemployment benefits, I just kicked out everybody who's unemployed. I'm gonna get some really weird results, right? So I have to kind of be worried about making sure I have a variable when I'm taking the natural log. If I want to make comparisons, I need to make sure that I still have the same sample size, okay? That I'm not losing observations there, okay? Any questions on this? We're kind of go back to the slides here. All right. So, what if we can't compare? This is not a great answer, but we have to make some kind of reasonable assessment of what the relationship between two variables are. So for instance, if I was thinking about the probability, or let's say I was trying to estimate how much money was spent on mutual funds in a household, right? So I want the level of investment they're making in mutual funds. Well, there, if I'm thinking about, if I go from $50,000 to $60,000, right? That's not going to be the same as if I go from 250 to 260. Because when I'm going from 50 to 60, I might still buy a lot of necessities. I don't have a lot of money laying around to kind of put in savings, right? And so if I'm a household making 50,000 out of 60, maybe the amount invested doesn't change hardly at all. I'm using that to make house upgrades, right? Or buy a newer car, right? Now that same $10,000 increase in income, if I'm going from making 250 to 260,000, I likely have already been able to purchase a lot of the things I need. And so what am I more likely to be able to do? Take that entire 10,000, put it in savings. So there's that same $10,000, that same unit change is likely going to cause a very different amount invested into these mutual funds. So what might I be more concerned with? Maybe I'm thinking about, I want to know more about percentage changes, right? Percentage change in the amount invested. So maybe I want my dependent variable there to be kind of the amount invested in terms of percentages, right? But I won't try to ask, I won't rely that we have knowledge about the relationship between these variables, but in practice, if we can't compare the models, we have to make this judgment call, okay? So, we've got a bunch of different, we got one more thing we'll talk about we're just gonna kind of work through things we've talked about just in a different example. So I'm gonna go back to Stata here. I'm gonna open up this one I did remember to put in here. So week 9, happiness, right? So I had this variable, the data set. I've got hours worked, the number of children, age, and then this like self-reported happiness measure. So I don't really remember off the top of my head exactly what this looks like. So kind of good practice. I'm just going to summarize it. So it looks like it was kind of this continuous measure. It was somewhere between like 1 and 3, right? So I had this happiness measure. How happy are you with your current life? Higher levels meaning I'm more happy, right? It's kind of a weird variable, but let's go with it. Like we're trying to estimate someone's happiness, okay? So I'm going to go over here, and I'm just going to run this regression where I'm trying to predict someone's happiness with their hours worked, children, and age, right? So if I were to run this regression ahead of time, what do you think is probably true about the slope coefficient on the hours worked and happiness? Holding constant someone's age and the children they have. I don't know. You could tell a story either way. Working more gives me more money. I'm not controlling for income here, so maybe that brings me a high level of happiness. Maybe I have a sense of like, what am I looking for? Like I feel like I'm a contributing member to society. So I think probably positive. Children, I hope they're positive, right? I hope that coefficient is positive, that they bring more happiness. And then age, it could go either way. I generally think about older people are kind of crotchety. The older I get, I know things set me off a little bit easier. So maybe it's negative there, but I don't know before running this. So I'm going to run this regression. Okay, everything here actually looks like it's positive. Okay? So having an additional child increases my happiness measure. Once again, this happiness measure is kind of just weird 1 to 3, so it's a pretty small kind of change. Hours worked, every additional hour worked on average, I think this was weekly hours worked. So if I go from like 40 to 41 hours worked in a week, increases my happiness a little bit. Age being 1 year older increases my happiness a little bit. Now, all these are relatively small coefficients, but all of them, at least at the 10.5% level, are what? Statistically significant, right? They all have p-values at what are 0, 0, and then 0.018. So not quite, age is not quite statistically significant at that 99% level, but pretty close. So here would be like my level, or my linear model, right? Everything's in linear terms. Everything's in units. So that was what I was going to say. 1 year older, 1 more child, 1 more hour worked on average each week. So I'm going to think about then a quadratic relationship, because I think about, if I'm thinking about having kids, which I'm very thinking about a lot lately, right? Going from 0 to 1, I imagine I think I'll be a lot happier. If I was to go from like 4 to 5, I'm not sure if that's still positive. I mean, hopefully, yes, it's still positive, right? That's going to be a very different effect. So I'm thinking, maybe there's this like quadratic relationship. Initially, like it really increases happiness, but then once I have 4 or 5 kids, the 6th or 7th kid doesn't increase as much. This sounds terrible to say, but this is how economists think, right? I'll also kind of have this square term on hours worked, right? Yeah, initially working more hours, I'm increasing my income, but at a certain point, if I'm working 80 hours a week, that 81st hour is not providing me with a lot of additional happiness. I'm already worn out. So I'm going to create these 2 squared terms. Now you can do this. I think I've got it down here later on. You can do this using that shortcut I showed you last week, which was that C dot and then the double hashtags. I would stick with creating the variables. I mentioned that like in practice, we don't like to do this because we don't want to blow up our data sets if we have large data sets by adding a bunch of variables. But I think it just makes it easier. Like if you're naming the variable squared, and like it just makes it easier to kind of keep things less black boxy, I guess, so to speak. So I'm going to create these 2 squared terms. So children times children, hours worked times hours worked. I've got some kind of missing values here. It shouldn't matter. I'm guessing I had some zeros. Those shouldn't have been in my regressions anyways. But then I'm going to come down here and I'm going to try to estimate just this hours worked to see if it should be kind of modeled as a squared term as well, a quadratic model. So we had our original model. I'm going to run that just so we have it for comparison. I'm now going to run this model where I use hours squared as well. Now, if I'm looking here, having this hours squared, would I say that adding a square term has a statistically significant effect at what levels? p-value is 0.02, so statistically significant at R 10 and 5, right? It's going to be less than an alpha of 0.1 and 0.05. So pretty strong evidence that this quadratic term has some good predictive power about our y variable or our happiness. Now, kind of similar to our intuition, if this is positive, right, that first linear coefficient is positive, the squared term is negative, that means that as hours worked increases, that marginal effect, what is the happening to that marginal effect? So, kind of reviewing things here, but what would the marginal effect be of anything? So here I've got happiness, excuse me, and I'm just going to write out the hours worked variable here. Well, what's the marginal effect? If I take a derivative of y in respect to x here, beta 1 plus 2 beta 2 times hours worked. So if this was positive, this is negative. As hours worked increases, what's happening to my marginal effect? If this is negative, as I work more, the marginal effect is I'd be adding a larger negative value. So my marginal effect is going, no, it's somewhat early, but I have an 8 a.m. and they're more responsive than you guys, right? Larger negative value, my marginal effect has to be going down, right? So I know that when I'm looking at higher hours worked here, it looks like it's kind of tapering off. That marginal effect isn't as positive as it was at lower levels. Now I could estimate this marginal effect at different values. So maybe I want the marginal effect for if I'm working 40 hours a week. All I would do is plug a 40 in there. Maybe I want the marginal effect of another hour worked if I'm working 60 hours, right? So I can do that in Stata, right? So here, I've kind of got that hours worked variable, right? And it's square term. I'm going to go down here. So we already ran this regression. Oh, yeah, I have it right here. So here I've got, I want the marginal effect. So you don't have to do it this way. If I ask you to do this on a problem set, if you want to write it out, type it out in Word or type it out in the comments and actually grab the coefficient. So how would I determine the marginal effect for 40 hours worked here? Well, I would go take the coefficient beta 1. I would add to that 2 times the coefficient on my squared term, beta 2, times the hours worked I wanted the marginal effect of, which was 40, right? All I'm doing there is grabbing those values from Stata and then plugging in the value of x that I'm interested in finding the marginal effect for. I can also do this. I noticed a couple of you kind of done this along the way when I've asked you to do certain things, although we didn't really cover it necessarily in class. Anytime I run a regression, I can use the coefficients from the regression that I just ran. Now, once I run a new one, all the old ones kind of go away. But notice here, if I run this regression, this underscore b, and then putting in like these square brackets, whatever the variable I want to use the coefficient of. So here, I want to use the coefficient of my hours worked variable. That was beta 1. Then to calculate my marginal effect, I want to add in 2 times the coefficient on my squared term. Now here, this is why also I think if you want to use this method, writing out a new variable makes this part a little bit easier as well. Because now I'm like, okay, I want the coefficient on that hour squared term. And then I need to multiply that by whatever I want to find the marginal effect of. Here it was the marginal effect of 1 more hour work starting from 40 hours a week, right? So I used 40 here. You could do a similar thing. Maybe instead, oh, if I can, there we go. Copy, paste. I'm going to also look at what that marginal effect is if I were to work 60 hours a week. So what's the effect of 1 more hour's work if I'm working instead of 40, 60 hours a week? We would expect that marginal effect is going to be, we said if that square term has a negative coefficient, and for higher values of our work, our marginal effect should be smaller. So all this is going to do, this display command, is it's going to take those values that are stored behind the scenes and do the math for you. So you don't have to worry about rounding to certain decimals. You don't have to worry about typing it out wrong. you can kind of get this to show you the marginal effect pretty quickly. So I'm just going to run both of these. And what I'll see here is, sure enough, that marginal effect of an additional hour, when I work 40 hours a week, it was 0.002. At 60 hours a week, it's down to 0.0008. Okay. Any questions? So I won't expect you to do this on the problem set. You can do it by hand. But if you're wanting some additional like practice coding and thinking about how we can use the stuff that is stored behind the scenes, and actually, this is moving away towards like if you go work for a company and you start doing everything by hand, they're not going to love that. They want you to start to use the new technologies. This would be kind of our movement toward that.
Is that marginal effect when you're holding like children at age constant?
Yep.
If you wanted to, could you do like marginal effect of 40 hours with like 2 kids and like,
So that,
or is that not?
what you're thinking about, you're jumping to next week. So that would actually be that the effect changes depending on another variable. There, we're actually going to start using what we call interaction terms. You can't pick that up just using the marginal effect calculation here, because this is just the effect of one more unit of that X variable, hours worked, holding constant the other things. If you think that effect, like you think working an hour has a different effect if I have 0 kids versus 1, is that kind of what? Yeah. Well, there I have to create an interaction term between those two. We'll talk about that next week. Yep. Right now, we're just thinking about holding everything else constant. What's the change in that marginal effect for different values of that X variable? Yep. Okay. So one thing we also talked about last class is if I want this marginal effect, if this is positive, at some point, this marginal effect, if it's going down, at some point it goes from being positive to being negative. So we said we can figure out where that point is by setting this equation equal to 0. Where does that marginal effect essentially switch from being positive to negative? Well, wherever it is equal to 0. You're thinking about visually. Where does that marginal effect switch from being positive to negative? Okay. So if I rearrange this to be able to solve for the hours worked, I get what? Negative beta 1 over 2 beta 2. This is going to give me where that turning point occurs. Okay. Now, because beta 1 is negative, or sorry, beta 2 is negative here, the negatives will cancel and we'll end up with an actual positive amount here. So, but we do have a negative sign out front here that we need to not forget about. So I'm going to do the exact same thing. Once again, I could do this by hand, right? I know that I'm going to take beta 1, the coefficient on the linear term, negative beta 1, divide that by 2 times beta 2, the coefficient on the square term, and that should give me that turning point. Well, what does that look like using this kind of like display? I can take that coefficient on hours worked. Now here it's a little tricky because one thing I forgot to add in here, oops, is it's negative, right? I then need to divide that by 2 times that coefficient on my square term. Okay. So if I do that, that should give me, oh, what didn't it like there? Oh, because I put this in. I guess I can't use parentheses. I forgot the syntax of how this works. So let's see. There we go. So this is very, very high, right? At 60, it was still positive. We would actually need to get to an hour's worth of 73.7 for it to actually become negative. So in reality, are we ever going to see anybody working a number of hours a week with the marginal effect is negative? Probably not. I mean, I'm sure someone out there is working more than 70, truck drivers or something like that. Sometimes we'll log 80 hours a week. But that turning point's pretty high out there. Okay. Any questions? Once again, you can do that by hand on the problem set if you want, but you can also kind of use those coefficients and do the math using this display command in Stata. Okay. Any questions here before we keep moving? So I did this exact same thing, and you can figure out, like, use the coefficients. So notice here, if instead of creating the square term, I use that C dot command and then double hashtag C dot, the same variable, it creates the squared term for me. you know, actually, why does it look a little bit different here? No, it's the exact same values, right? 0.004, 0.0003. So I'll get the same regression results, doing the same thing. It's just only temporarily creating that square term. And then also, if I wanted to use this method of using the coefficients, notice if I want to take the coefficient on the square term, it's now like this much longer, like it's C dot, hours worked, pound sign, C dot. So I can do that, right? I can still use that coefficient. It just gets, I don't know, a little bit less clear. Like, is that the quadratic? Like, how exactly, what's the syntax? That's why I always just like to create the square term, because I know the name of it. It's a lot easier for me to kind of use it moving forward. But you can do it just to be completely transparent using that C dot command as well. Any questions on that before we keep moving? All right, so we got our squared model. I'm then going to look at, okay, here's these different variables: happiness, hours worked, age. I want to take the natural log of all of them so I can start to look at some log linear, log level, or linear log model, log model. Okay? So I took the natural log of my hours worked, my happiness, and my age variable. So the first thing I'm going to do is, okay, should I be modeling this relationship between happiness, hours worked, and actually, no, not hours worked. What did I take? Yeah, log of hours. And age, should I be modeling hours worked and age as not linear, but nonlinear? So I'm going to run the regression where I include both the nonlinear and the linear terms. I can then use these F tests, right, where I test the nonlinear terms and then the linear terms. Now, we did this before in an earlier example. So notice in this scenario, when I test the nonlinear terms, the natural log terms, what I'm saying is I'm going to start out assuming those natural log terms, nonlinear terms, had no effect. Can I reject that? So can I reject the joint significance of these natural log variables? The p-value is 0.4, right? Is that anywhere close to being? No, so I would fail to reject. So what did I assume was true? That the coefficients on those nonlinear terms was 0. I failed to reject that. What I'm essentially saying is those nonlinear terms don't have any impact on this y variable. So they shouldn't be used. Or my nonlinear model here isn't as good. Now, if I look at my F statistic, or the kind of joint significant test for the linear terms on hours worked and age, well, there I've got a p-value of 0.018. So at least at the 10 and 5%, I could reject the null. So there I was assuming the coefficient for hours worked and age, right? Those were equal to 0. I'm rejecting that, or essentially saying that the linear model does explain some of the variation in my dependent variable. So this would be evidence using kind of this F statistic and this F test, right, for joint significance, that we should be using the linear model, right? Because that's the one that we could reject those two coefficients were jointly equal to 0, right? The other one we failed to reject. So this one was a little bit more clear than the last example we looked at. The last example, we said sometimes it's not as clear. We have to base that off of whatever has the highest F statistic. Here, what has the highest F statistic? That linear model. And it's the only one we could actually reject. Okay. So just another example of something we talked about earlier today in class. Let's think. What do I want to do next? So let's say instead of, well, we did joint significance, right? But what could happen is this method of using joint significance, where I'm looking at should multiple variables be nonlinear, maybe it was the case that hours worked should be linear, but age shouldn't. So I'm now going to think, okay, maybe it was just, here's my here's my level regression, right? Where everything is in levels. And then here's my regression where I've taken the natural log of hours worked. Because earlier, we had some evidence, right, that hours worked wasn't linear. We had evidence that it was actually a quadratic model. Right? So if I tried to estimate this as a linear log model, I can start to compare this, right? So I look here, okay, Well, if I model this as a level log model, ours looks like it has a statistically significant effect, right? When I use the natural log of it. However, if I want to compare this to my quadratic model, or where I was using the squared term, well, my R squared here is 0.0019, or sorry, 0.0016. If I go back to my squared model, way up here, what was my R squared? 0.002. However, I didn't want to quite use the R squared here. Why? Because if I'm going from this model where I had a squared term to the one where I was just taking the natural log, what did I essentially do in the squared term model? I added a variable, so I know the R squared should be higher. So what should I really be comparing? This adjusted R squared. So the adjusted R squared from the quadratic or the squared term model is 0.0018. From my natural log or my level log model, it was 0.0015. So I get the same decision in this case, but notice the gap in the earlier model between R squared and adjusted R squared was like 0.002. Here it's only 0.01. There can be situations where if you use the R squared, you'll make a different decision than if you use the adjusted R squared. So we want to make sure we're using the adjusted R squared anytime we're comparing any model to that quadratic where we had that squared term, because we're essentially having more variables in that model, right? So there we use our adjusted R squared. Is there anything else I want to say here? I don't think so. Any questions for me or think about anything else we could do here that you just have general questions on? All right. So I've talked about using the R squared, also using the statistical significance. So in this example, we said the R squared suggested we should be using that level or linear model. We said we could also kind of compare the statistical significance. The only downfall was if I compare that to the quadratic model, well, I've got two coefficients. I can't really compare those, right? So we have another type of test for whether or not we should be using the linear or a log term. So we'll introduce it here, and then I'll show you what it looks like in practice, because sometimes I just see words, it's easy to just get lost. So it's called a Davison-McKinnon test. So what we'll do, if we think that instead of a linear model, it should be a linear log, we'll estimate both models. So I'll run a regression where I try to predict y using just the regular level of x, and then another one where I estimate it using the natural log of x. I'm then going to make predicted y values for each one of those models. So we'll see what that looks like in a second. So all I would do is go through every observation based off the coefficients. We can always predict what y should be. We did a lot of this in the first half of the class. There's a way to do this in Stata that stores it behind, stores it as a new variable. So when we have this new variable, which is the predicted y values, we'll then use those, run them in the opposite regression. So if I have my linear model, I'll take the predicted y values from my linear log model, include them as an additional variable in that level model, and then look to see are they statistically significant. So I think this might make a little bit more sense to see this actually done in Stata, right? So what I'm going to do is run this regression where I'm kind of just doing this as my linear, or I said another kind of word I'm using is this level model. Okay? So I'm going to run that regression. I'm then going to use this predict command. Now, what the predict command does, it's going to take those coefficients, and you can do this with not just one x variable. Here I've got multiple controls, right? So what it'll do is it'll go through for every single observation based off of these coefficients. It will make the predicted y, it'll save the predicted y value. So I have my actual y, I have my predicted y. So if I wanted to, in fact, here I'll do this. I'll use this predict command. And we can take a look at this. So my actual y value was happiness. My predicted y values are right here. The difference between the two would be my what? Actual y minus my predicted y would just be my. So this is something that we use very early on in the regression. If I take the actual minus the predicted y, this would just be my error term, right? That's how much my predictions are off by. So we've got our predicted y values, right? I stored them as what I called model one. So this predict command, you first tell it, what do you want to call this new variable, right? You're calculating the predicted y value for every observation, but what do you want this new variable to be stored as? I called it model one, right? It was the predictions from my first model. Now this comma xv, that just tells us to go through and take the coefficients, multiply it by the x values, right? Just how we would always make our prediction. There's some other stuff you can do outside the scope of this class, but we have to, this is just the syntax to kind of do our basic regressions that we're at the level we're at right now. So I'm then going to run the second model, right? So this is going to be, we'll kind of call this, oops, model one. My second model is a level log model. We'll call that model two. So here I'm going to take the natural log of hours worked. I'm then going to make predictions from this second model. So one nice thing doing this in Stata, if I wanted to make predictions, and I won't make you do this, but if I'm making predictions where I have natural logs, I can't just use the x values. I actually have to use the natural logs of the x values when I'm making my predictions. Stata can do that behind the scenes for us pretty easily. Kind of a pain to have to do that by hand, right? You know, I mean, we can take a natural log on a calculator fairly easily, but it's an additional step, right? So I've now got my predictions from model one and model two. What I'm going to do is I'm going to run model one. So notice it's my level model, keeps hours worked in terms of units. However, I'm going to include the predictions from my other model that wasn't linear, right? So I'm going to run this regression where I now have the linear terms coefficient, my control variables, but also the predicted values that came from my nonlinear model. If I fail, you know, essentially, what am I assuming for that coefficient on those predicted values? I'm assuming if it's equal to 0, that second model had no additional explanatory power for my y variable. So if I can reject that null, I can reject it at 0. What that's really saying is that model 2 provides some additional amount of explanation of the variation y, that it actually was useful. Model 2 is more useful. Now here, my p-value is 0.64. So can I say that those predicted values for my second model have any additional explanatory power? No, right? I failed to reject. This would be evidence that model 1 was actually better, or that my linear model was the one I should be using. Now, if I do the same thing, I run my second model, but I use my predicted y values from the first model. Well, now notice here, when I'm looking at those predicted values from my first model, can I reject the null here that they have no additional explanatory power? Well, the p-value is 0.018, so at the 10 and 5% level, I can reject that they had no additional explanatory power, which would be evidence that they did have some, which is telling me that model 1, those predictions have a statistically significant effect. Model 1 should be the model I'm using. And that was our linear model. Right? Now, the reason why this test is kind of so powerful is if you think about it, you're saying hold constant the linear aspect of hours worked. Does the nonlinear aspect have any additional explanatory power? If it doesn't, then we should just be using that linear term. Said differently over here, hold constant the nonlinear aspect or the nonlinear effect of hours worked on happiness. Does the linear component explain more variation? Well, here we can reject it also. It did. So once again, this would suggest that model 1 was the model we should be using. This, any questions? I know this is kind of confusing here. Yeah.
When you include like model 1 and model 2, right? You're not saying that a change in model 1 changes the intercept or anything, right? It's just there as like
Yeah, I won't ask you to interpret this, but the way to think about it is holding constant the predictions that my second model are making, right? Holding constant the things in my model that would predict y. Would the predictions from my other model be any better of a fit with the values I'm seeing for Y, or have any additional explanatory power for those values that I'm seeing in Y. So because we are still including that natural log term for hours, it's like holding that constant. Does the other model have an even more explanatory power than this current model that I'm looking at? Because I'm holding constant everything else in this second model when I'm thinking about the interpretation of the coefficient model. I would never ask you to interpret it because it does get kind of weird.
I'm just confused, like what it represents in this, like progression. But
What model one?
yeah,
So if we're thinking about what we're doing here, so I had kind of model one was y is equal to, and I'll keep the constants out just to make a little more sense. So it was like, it was just the linear model. So I was getting these coefficients and then obtaining predictions for y from model one. My second model, I was taking the natural log of x, and I could just run this and say, okay, what's the impact of that nonlinear term? But I'm now adding in the predictions from my other model. So what I'm essentially saying is, does that other model have any statistical significance, or can it explain more amount of variation y at statistically significant levels, even holding constant what would have been my predictions from model two, right? So if this can provide additional explanatory power, what I'm essentially saying is, compared to just having this second model, the predictions in model one allow me to explain more motivation or had a statistically significant effect. Therefore, model one must be a better model. Does that help make a little more sense? And then you can do it the exact opposite way as well. I can take model one, add in the predictions from model two. Now, what is this saying? Compared to the predictions I'm making just using the linear terms, did model two, where I was using nonlinear terms, did it explain, right? Or did it have a statistically significant effect on the variation in y? Well, here we said that we failed to reject. So that was suggesting model two isn't any better than just using our predictions from model one. This might be another way of thinking about it. I get this is tough. Yeah. Does that help a little bit?
yeah. But are you using like R-squared at all, or are you just looking at that?
Nope. So by controlling for the linear term, it's a better test than just comparing the R-squareds. So if we end up so in this case, so I understand your question. It's good. So here, let me run this regression. If I use that model one, that adjusted well, here it doesn't matter. We compare R-squared adjusted 0.0018. That was the linear model. The nonlinear model was 0.0016. So the outcome that we determined using that McKinnon-David test, is it David McKinnon? Whatever it is, whatever the order of that test is, we end up making the same decision here as if we use the R-squared. There could be some situations if we start to add in a bunch of additional controls where the R-squared value, the difference starts to get really, really small, and we actually can't even see it in the output out to like the third decimal. And that David McKinnon test gives us a slightly better measure of whether or not the linear or nonlinear model is better. The R-squared is kind of like our initial, like, this is evidence, but what would stronger evidence be using kind of the outcome of this test? Yeah. Just like when we were looking at adding in more variables, we could compare the R-squareds, but we know that adding more, like, I need to make an adjustment still. This is kind of like making our adjustment. Yeah. Any other questions on this before we keep moving? So I've got some additional interpretation, just different things we could work through here. I might start with this and just revisit kind of this idea of nonlinear relationships, but we'll focus a lot more on interaction terms next class. One thing I did want to mention, and I think I mentioned this last class, but the whole reason why we're concerned with choosing the right model is because of this assumption that we made very early on, which is when we're estimating lines of best fit, we're trying to come up with a line that best fits this data such that no matter what value of X I'm looking at, I'm making errors above and below this value of X. Oops, sorry. I'm making errors above and below, but notice there's kind of equal amount of errors on both sides of my line of best fit where I'm making predictions. Or said differently, the difference between my Y values and my predicted Y values for different levels of X, the expected difference is always going to be 0. Or that line of best fit is kind of like perfectly splitting my scatter plot, right? So what's another way of saying this? Well, the difference between my actual and my predicted Ys, this was just saying that the expected value of my error term for different values of X are equal to 0. If I have nonlinear relationships, then if I try to estimate a line that best fits a scatter plot that looks like this, well, I mean, I don't know. If I'm trying to draw a line that kind of best fits all of the data, I'm kind of missing some here. For some values of X, I'm only making negative errors. My predictions are always too high. For some values of X, my predictions are always too high over here. In the middle here, some predictions are always too low. So the error term for different values of X here for my line of best fit is not always 0. It's actually always changing, right? So how can I get that expected value of my error term to be 0? I can allow there to be a nonlinear relationship. Now kind of my errors at every X value, I've got some above and some below my line of best fit, right? So this is the whole reason why we're concerned with model selection, is because one of those underlying assumptions we had about our linear regression results was that the expected value of the error term is equal to 0. If that doesn't hold, all of our coefficients are unreliable. How can we make sure our coefficients are reliable? Make sure that violation, make sure that assumption isn't violated. We can allow there to be some nonlinearities to this relationship between X and Y. And then what we've been talking about is how do we figure out which of these nonlinear relationships best fits it. So we'll pick up on this next class. We've really talked about everything that you would need to kind of complete that quiz or to kind of complete that problem set. Once again, it's not due tomorrow, so you can take your time, right? But I would start going to those practice problems, start looking at that problem set once I post it later today. Get started on it early. Want you guys to get as many points as possible, right? So feel free to ask me questions as you're working through those. Otherwise, we might revisit this, but we'll really pick up on interaction terms on Thursday's class. Unless there's any other questions for me, we'll see you guys on Thursday. Don't forget, I reopen that additional midterm assignment. You can turn it in by the end of the day today. I'll get started grading those tomorrow. Okay.